Good morning and welcome to this Micrographics webinar. Today we are covering skeletal modeling. Title shows us there, Skeletal Modeling Demystified. We'll be talking a bit about what it is, how you can do it, and looking at a few examples within Inventor. So the subtitle there is Top-Down Modeling in Inventor. Basically that is the style of modeling that skeletal modeling is. It's a top-down look, and I'll explain how that works throughout the presentation. I'm your presenter, Carl van Rooyen. I'm an application engineer with Micrographics, and my email address is here on the first slide, and we'll also have a slide at the end with some content details on. So this session is going to be recorded and then put up on YouTube at a later date, so you'll be able to refer back to this as well. And right at the end we'll also have a Q&A session, so if you have any questions you can just hold on to those until we get to the end, and we'll then have the Q&A session at the end. So we'll move on to the agenda. On the agenda today, we're going to start with we're going to start off with a introduction before we move on, or an introduction to the top-down modeling, and we're then going to move on to planning your model, so how to plan your model out for that skeletal model. Then we'll go on to how to design your reference and part models. So looking at the reference model design and also part design. And then we'll bring it all together in an assembly. We'll also then look at what happens when you update your designs, whether it's updating from the reference or changing things in the assembly, before we close off with a summary and Q&A session. So moving to the intro, what is top-down modeling? Well, this is a workflow where the design starts off as a reference model. So starting on the left-hand side there with that reference, that would be a single part file that represents the layout of the final product. So you take that part, you design into it the basic layout of what you want to achieve. This layout will include information such as the position, shape, and size of parts within the design. And you would put all the relevant information in there that you can with regards to the design. Then from there, parts are being created from this reference, typically using the derive option to bring in the required information into each of those parts. So we can see there we have part A, B, C, D, and the reference part is derived to create each of those components. Now this layout information is brought through into the derives. It's then used as in the part geometry that is required. So that reference holds all the geometry that you are looking for your overall design, but you only derive into each of those parts what you need. So part A, B, C, and D just have the information regarding each of those parts. Then those components are placed into subassemblies, and then once those components are placed into the subassemblies, those subassemblies can be put into the main assembly. Now the structure shown on this slide is purely for representation purposes only, and can be changed as required. Parts A through D can be put straight into the main GA. You could only have one subassembly with some of the other parts straight into the general assembly. That structure is flexible. You change that as you need. Now, if you need to make any updates to this, those updates are made at the reference level. So you would go ahead and go back to the reference. Let's say you're changing layout, the position of certain components that are driven by the reference. You go back to the reference and you update the reference. So that update is done at the reference part level, and then they are carried through the design through that derive all the way up to the main general assembly, and those updates are automatically carried through those components, removing the need to do manual updates, like changing a shaft diameter, then having to go find all the bearings and changing each bearing diameter individually. So that is the basic to top-down modeling, where you are creating your layout first, and from there you are generating your components from that reference part or layout. So the first stage of that top-down modeling approach or skeletal design is planning your model. So I always advise designers to take the time to think through a design before starting with it. Now, whether it's a simple part or a complex assembly like we have in the image here, pre-planning is, pre-planning your steps, your design as far as possible will help the process. And this is especially true when you're embarking on creating a skeletal-driven model or a top-down model. So what you want to do is pre-plan the layout of your reference part, and this helps you understand the complexity of the task at hand. So firstly, you're understanding your design in its whole. You're not just starting with little bits and pieces of it and trying to piece them together as you go. At the same time, you can hash out your design intent. Now, your design intent, this is where you make decisions on what is driving the model creation, what is driving the geometry of this design. If we look at this image as an example, now the width of the conveyor belt in this design is driven by the width of the pallet that it needs to move. So that those conveyor rollers need to be wide enough for that pallet to fit on. So that pallet is a driving factor. The size of that pallet is a driving factor in this design. So we can pick that out as something to be important and include in that reference. Once again, if we're looking at the height of the opening going into that machine, that is driven by the height of the barrel on the pallet. So once again, there's a sort of a parameter or a design constraint there that needs to be met. And these are the types of considerations that need to be built into your skeletal model. These will also help you figure out the required geometry for the skeletal model, as well as what parameters you should use to drive the geometry. As I said, we've got the width of the pallet, the length of the pallet, the height of the barrels, the height of the pallet. Those are all parameters that can be built into the skeletal model that will help you drive the shape or size of the design. So those are things that would need to be considered when planning the model. So one thing to also look at with planning is your modeling considerations. How are you actually going to design this up? Are you going to use a single skeleton file? If we look at this assembly here, we have the conveyor belt, we have a platform, we have that packaging machine which has the blue upper section, the white lower section. Are we going to try and put all of that information into a single reference or skeleton file? Or would you rather break that up into multiple sections? Maybe the conveyor belt as a single skeleton file, the platform as another skeleton file. But from there, have shared geometry. Create a single skeleton that maybe has the overall layout, and then from there derive what you need into a separate skeleton file for, let's say, the conveyor belt, and then make that file more complex. So you take into consideration that. Are you going to mainly use derive to pull information from your skeleton file into the parts? Where do you need to use adaptivity? During the design process, you may need to bring information from the assembly back into the reference or into those parts. And we can't derive an assembly into a part and then put that part back into the assembly, it creates a cyclic loop. So that is something that's not allowed. And those considerations have to be thought about up front to prevent any issues in the modeling process further down the line. So you might have a mix of derive and adaptivity. Also, you may decide that some of your skeleton files or your skeleton file may have multiple bodies in it. And so you'll have a part file with multiple solid bodies in. And, how do we handle those multiple bodies, especially when it comes to creating out the parts and assemblies and sub-assemblies? You have to think about the structure of those. And also, during the planning of the model, look at the design and look at what design accelerators you can use within Inventor. Look at things like frame generator. What information in your skeletal model can you include to help create a frame generated component? And if I look at the machine guarding here, we have posts that could be generated in frame generator, created in frame generator. There's sections on the conveyor belt that can be used in frame generator. So the bolted connection is another big one that could be used. So think about those accelerators that are available in the assembly environment and what information you could include in the skeleton model to help the use of those design accelerators. And then also consider how you're going to use library parts, whether it's from Content Center or from an external supplier, a buyouts library with things like pumps, motors, hydraulics, cylinders. How is that information also going to be included in your model, and how are you going to use that? Something I typically find is I may bring in a library component into the assembly and then use cross-part projection, which creates adaptivity between that component and the part, that library component. Let's say it's a stepper motor. We'll actually have an example of this later on. You have that stepper motor that you could bring in and then use adaptivity and cross-part projection to affect the geometry of your part that's in your skeleton model. So, those are some considerations to look at when planning the model. And what we'll look at next is the reference model, the skeleton. How do you go about designing that skeleton? In the image here on the right-hand side, I've got a skeleton model here with a couple of sketches in it. And this is kind of the start of the layout. This is actually a CNC router, and the sketches there represent different components or different portions of the router. Some of them are quite simple. If we look at the base, and I'll go into Inventor just now and look at this, but we can see there is a blue square or rectangle which represents the bed of the machine. There is this yellow geometry on the left-hand side which represents a part, a riser for the gantry of the machine. So, this reference geometry is made up of mainly sketches in this example, but you could also use solids as well, or even surfaces. The surfaces are probably one of the best things to use in skeletal modeling, especially if you have a lot of sheet metal components, because in your skeleton, in that reference part, and you'll hear me use those two words sort of interchangeably, that reference model part or that skeleton, kind of use those interchangeably. But having surfaces in there gives you an idea of the volume of space required, but also especially with sheet metal components, it's very useful for creating faces or offsets to create a sheet metal component. And what you want to do here in your reference model is get that general layout of the component. So in this image here, it might not be clear, but I'll go into Inventor and we can look at it, is that we have the layout of the CNC router. There is the sketch for the bed. There's sketches for the supports or risers for the gantry. A simple sketch across the top of the gantry, a single line here represents the main beam that would go across the gantry. And then this mess of a sketch on the inside here is a 2D sort of side view of the carrier for the Z-axis on this machine. And so that there actually has a lot more detail within it to generate multiple components from that one sketch. And what this does is it assists in aligning components. You know, we can see how the width of the this riser here on the ends, how that width interacts with the width of the bed. We'd be able to see at this early stage, you know, if we keep that width at, it looks like 250 on that sketch, how much travel would we get on the machine? You know, where would the center line of the cutter be in relation to the bed of the machine? So we're already looking at aligning components, getting a general layout of this machine, and getting a better understanding of its mechanics right up front before we've even created any solid components. Because we've created these sketches that give us that general layout. And without a lot of effort, we're able to troubleshoot potential issues right up front before we're invested too much time into the 3D design. And, you know, at this stage, you want to keep things as simple as possible so that you're able to get a quick layout done, troubleshoot any issues, you know, maybe rethink your approach, and then start adding more complexity to the model. And if you find that something starts to get too complex, you could always, you know, derive out information from this reference component into another one. You know, so this really complex sketch here that's in the center of the gantry, that could have potentially been a separate part, which purely had just that line that represented the beam for the gantry as a start point, and then pulling in or drawing in the rest of that information. So you start to see where you can split things out to make life easier for yourself, but also getting that layout for the machine right up front in your skeletal model. So we're going to go into the software. You know, I'm tempting fate here and doing live demos on the webinar, but you know, here you're getting a sneak peek at kind of the end product of that top-down design with a couple of tweaks that need to be made. But I'll go back to that reference component and we can have a quick look at what we're seeing here. So, you know, we have a sketch. If we go into the top view, we have a sketch that represents the length of the machine and the width of the machine, and you'll see that that's actually linked to parameters. This is part of the planning phase, you know, deciding on those parameters for the machine. If I go into a side view here, we can actually see the side profile of the gantry sort of riser or support, as well as this mess of a sketch at the top here. Let me just quickly set dimension visibility off and we can see a few more bits and pieces here. So there's a couple of different plates, but that can all be used to generate out those components. What I'd like to show here at the moment with this example is the parameters. You know, I've created a couple of parameters here that drive the overall layout of the component. So if I look at this machine, it's 1.5 meter in depth. So we'll go to the parameter here for the, in this case, using the rail length as a driving factor. So you can purchase a 1.5 meter rail. So, you know, make the machine fit that size. So I'll change that down to 1,000, and the bed of the machine then updates according to that. And any other link geometry would update as well. So this is, you know, just using parametric design to drive the dimensions of the model. Now, if I need a wider machine, take that, in this case, the X-rail length, I'll update that to 1,500. And we see the width of the machine update. And these updates can basically be pulled through, and we'll talk about this at a later stage, to the rest of the model. And so I mentioned earlier about the barrels and the pallet width and length, those parameters could be included in here to drive the overall size of a machine. In that case, it was a conveyor belt. In this case, it's a router. So here we're looking more at the working area, what is available to work with. So we're looking at various parameters with regards to the bed width, bed depth, height of available, or machining available height, things like that on the design. So we create that skeleton, and then from there we would then start to pull out and create the components of the design. So the next section of the presentation, we would look typically, or we would be looking at part design and how would you go about designing the individual components. So we have that reference with all the different pieces in as far as the sketches go, but we now need to pull out and extract just a certain piece of that and generate a single component. So typically you would use something like your derive, where you derive in the reference part and you bring in the information that you need. So things like sketches, solids, surfaces, even parameters can be derived from that skeleton into your model. And then you use that derived geometry to then design the component, to create that component. And the nice thing about this is because everything's derived from that main skeleton part, that main reference, you're basically doing what's called in-place part design, where the components are all designed with reference back to a shared origin point. And that makes reassembling this a lot easier at the end of the day because they have that shared origin point, much like automotive makers design cars. Every single component in the car has the same origin point within the vehicle. And so this uses that idea to make assembling the components a lot easier. So one thing I want to just go back into Inventor and look at here is under the parameters, we have some parameters for the thickness, and I am missing a parameter here. So what I want to do is add that parameter in, and I'm going to call this the riser underscore thickness and make that 20. So that is going to be the thickness of the material used to create the riser. Now, granted, I already have that riser created. If I open up this piece here, and I'll go through how this was brought in. We can see that because I updated the main model, it's asking for an update here, but I'm going to just right-click on that derive option, and looks like I need to update that first before I can edit it. So I'll do the update and then edit derive part. So using the derive feature, I brought in basically just the sketch that represents the profile of this part that was needed. And what I'm going to do right now is I'm going to add that user parameter that I've just created in the skeleton part. So there's the riser thickness. So I'm going to add that parameter now to this part as well. So if I go into parameters, we can see here that riser thickness is a linked parameter. And up here on the thickness parameter, that is on our sheet metal rules, I'm going to put in there riser underscore thickness. So now that parameter is linked through to the thickness of this component. Making that change updates this component, updates its thickness. We can double check this on the sheet metal defaults. You can see the thickness there is overridden to the riser thickness. And so now if I needed to make changes to both risers, I could do this on the other side. And then once that's implemented on both sides, changing that thickness is quite easily done from the single point, this skeleton part. We can go ahead here and change that over here, hit done, and then update either the main assembly, or I'll go directly to the part here and update it in the component. So you can see there it's now asking for the update. Go ahead and update, and then the thickness is updated on there. So pulling that information through that is required to create that part. You can see in the image, the part was initially derived with the sketch, and then using the sheet metal face option, that sketch was then faced to create a thickness, as we just saw now, that thickness parameter that I pulled through. So there we have the, sort of the intermediate part of the design that's just straight after the face thickness was added to the sketch. And then from there, more information can be added as the design progresses. So I've already kind of skipped to that demo part already. So we can see there we've got the derived feature, the face, and then what we haven't seen up to now is how the holes were created and the cut here as well. But we can see these holes are locked. These were created using the bolted connections, and then the cut is adaptive. We'll go through how those were created in a few slides' time. So kind of jump through the demo already on this one. So we'll go ahead to the Assemblies option. I just want to see why that, there we go. So once you have, once you've created that part, we would then need to place that part into, let's say, a subassembly. So here we're looking at a subassembly on the right-hand side where we have the that riser plate with a set of bearings mounted to it. And in this case, we've made the use of place grounded origin to make sure that this plate is placed in its correct orientation with reference to the rest of the assembly, once everything's brought back in. And then in this case, we're creating subassemblies as needed. So we're making use of place grounded origin within a subassembly, in this case of this subassembly that's shown on screen. And if you're using multi-body components when processing out the solids into parts, just be aware of your assembly structure. Typically, if you want to create any sub-assemblies, you would need to push those multi-body parts out separate as sub-assemblies in those groups, should I say, and then assemble them all together. And I'll run through an example of that in the design here as well. But taking all the components that you've designed, make use of that grounded origin, create sub-assemblies as you need them. In the case of this design here, we've got that sub-assembly. Wasn't using the multi-body method for this. And then, make use of design accelerators. As you are creating your assemblies, think about frame generator, think about bolted connections. Those are just two that I like to highlight, but there are other generators that can be used. And think about how those can assist in modeling. In this case here of this component, I used frame generator to create the holes within that plate and place the bolts down with reference to the holes in the bearings. So, the bearing there is a part that was downloaded off the internet from a supplier's website. It's then constrained into the model, and that once that's constrained in its place, the bolted connections in this case was used to create the countersunk holes and also place the countersunk and cap screws inside of those holes as well, the countersunk screws in those holes as well. And if you change the placement of the bearings, those bolted connections would be, or you would update the bolted connections, and it's basic two-click process to make sure that those are updated and in the correct location. Another thing to note here is to also use parameters to drive patterns and relationships in the assembly. So if we look at, once again, this frame here is created using frame generator, and the cross members across the frame, we've got what, 6 of them there, 1, 2, 3. We've got 6 of them there. Those are driven using a pattern and putting parameters from that skeleton for the overall length of the component, the width of those frame members that we used. All that information can be used to generate that pattern. So as you update the length, you have either more or less cross members that are inserted into that frame. Relationships as well, joints and constraints can also be driven with those parameters from that skeletal model. So think about how you can use that information to automate a little bit of the design. And if we want to take design automation a step further, you can make use of our logic. I'm not going to go into our logic for this webinar, but we've had previous webinars for our logic. You would be able to create design rules that specify that the spacing between these cannot be larger than, let's say, 300 millimeters, and it would automatically increment the number of cross members required. Also using our logic to create configurations. You could choose whether or not you want supported rails or if you want linear rails with your configuration. That would change the type of rail, in this example, the type of rail used for the bearings to run on. So look at the possibility of using our logic within your designs, but as a simple start, using parameters to drive things like patterns and relationships as well, especially with design accelerators included in that. So see, I'm missing a demo slide here, so what I'm going to do is just go back into Inventor. We see this single part here with with these holes already in, but if we look at the browser, you'll see that it's hole 2, 4, and 6 with a lock there. Now that lock shows us that, basically tells us that this was created using bolted connections. So I'm going to go ahead here back to the main assembly and open up. We can actually see that in the main assembly things have shifted. I haven't updated the main assembly yet to update those changes. That error that I'm getting is because of the bolted connection. It looks like we're having a small issue here with the gantry, but we can always fix that quite easily. I'm going to go ahead here and I need to change my component priority selection. Go ahead and open up this piece on the side. And we can see the bearings that are placed in here. If I just go ahead and open up the bearing, that bearing has an existing set of tapped holes in the model. So, this was in the model. I don't have to care about what that existing spacing is. I don't have to go and measure the spacing and decide or figure out what that is. In the model here, as long as I know that spacing is accurate on the model, we can easily go here to the bolted connection option on the design tab, bolted connection, and I'm just going to edit the existing one. This bolted connection is placed in our hole. So it's placed in using that hole on the downloaded library component, and we're following the pattern there, so it places down all 4 of them. And the bolted connection, once choosing the actual bolt itself and setting it up, will drill any holes that you need. So we can actually see here, it's going to drill the countersink flathead screw hole through there for me. So I'm just going to hit cancel here and repeat that 3 times, and it creates the different hole patterns that are required for that. And if you update the geometry, I have noticed one small thing. You would just need to come back into the bolted connection. I actually think it's a bit off screen here. If the spacing between those bearings update, I have noticed sometimes you do just need to literally right-click edit using Design Accelerator, and then accept it again to update that connection into the correct location. But it's a small thing rather than having to redo the entire sketch or altered connection from scratch. It's a short way or quick way of updating, making sure that that is in the correct location. In actual fact, what I'm going to do is go back to the reference part here, and that 250, that drives the width of that part. I'm going to change it down to 200. We can see what happens there. So we'll go to our parameters. There's the Y carrier width, 250. Change it to 200. You can see here the sketch has changed to 200. And we'll go all the way back to that subassembly. There we go. Just took a second there for the update to come in. And you see when I hit update, it's looking a little funky at the moment, but the bolted connections literally just need to be edited. You'll see it jumps back into position, hit OK. And I'll be honest with you, I don't know if this is an isolated case just on my PC or if this is the case for everyone, but you know, that was pretty quick and simple to update. And now we have that model updated with the new width. There's something weird happening up here, but I'm going to show you in the main assembly. We spoke about adaptivity. You'll see that this is an adaptive part. So let me go ahead and open it here. We can see that that cut is adaptive. So in the assembly, go back to the assembly, something has happened with gantry. Oh, there we go, it just needed to be moved. I think that's the frame generator having a bit of a wobble there. But we can see now that in the main assembly, I have placed in a stepper motor. Sorry, on the gantry. Let me open up the gantry. On the gantry here, we've placed in a stepper motor, and that stepper motor go ahead, yeah, close this. If I've got the files open, double clicking on them is going to go to the open file. So just accessing this, editing this part in relation to the assembly, you can see that that cut is based on geometry projected from the stepper motor. So there's a ridge on the stepper motor that allows it to be mounted or aligned with a hole or centered with a hole that is projected onto the part, and then the cut created from that. So looking at adaptivity here, just to edit the part itself a little bit as well. So we're not only driving from the skeleton side, but also from the assembly back down. Now, so I can go ahead and I can change a value here, and as we shift the brought-in library component, that hole shifts as well. So I can move that back over 10 millimeters to shift that hole as well. So, not only are you limited to working from your reference model up towards the main assembly, but you can also place components in the main assembly and change the design as required. Now, for those keen-eyed of you that have seen the rail is still short, that is just a downloaded model at a 1 meter length. I could have gone to the effort of redrawing that model and having its length update according to a parameter. You could have our logic that checks the length of the gantry, the parameter for that, and switches out the model, maybe removes this one and puts another one in that's the correct length. But you've got the various options available to you. I'm going to jump back into the PowerPoint, updating your design. In actual fact, this has kind of been happening as I've been working through. We've been seeing what's happened. So, you make a design change or a design update in the reference part, and that will then push through and update the geometry or parameters of the rest of the assembly. Now, those derived parts will pull that change through, and your components update according to those changes. And if you have any logic rules set to run when those parameters change, those iLogic rules can run as well. So as you make that change in the skeleton part, you can open up the assembly or sub-assemblies and have them update to reflect those changes. If adaptivity was used, the same thing. You change the placement of the part. That's what we just looked at with that stepper motor. As those parts move in the assembly, anything that is adaptive to that updates as well. So kind of been seeing that as I've been working with this, so I'm not really going to need to go into a demo on that. So what we're going to do now is we'll move on to closing off with a summary. And following the skeletal modeling process that I've outlined, in summary, we can basically say that following this process, you will get a good understanding of the machine layout early in the design phase because you are sitting down and planning the process. What does that reference model layout look like? Once you start putting those sketches and solids together for that layout, you start to understand the machine. In the case of this design, that CNC router, you start to understand how the position of the gantry affect, or the width of the gantry affect the travel of the machine, the position of the bearings. You start to kind of get an idea of how everything fits together. And so early on, you can understand the design and potentially pick up any design flaw before too much time is invested in the design. It also gives you a more unified design direction because you have that base skeleton to work from now. You've created the foundation to work from. It gives you a unified point, a single reference model, that next point there in the summary. Now that single reference model to go back to and refer to. Even if you have multiple designers working on something, they are all deriving from that same single reference model. And so if there's a change in that reference model, their models that they're working with will update. They can then adapt what they're busy with to those updates. So you have that single reference. And once again, it's easier to assemble due to the design in place approach. I didn't really demo that, but using the place grounded origin option allows that placement quite easily of components within the design. And then from there, you can sort of relax some of the constraints or constrain it into position if you do need movement. And then it also allows for updating of multiple parts at once. I mentioned it earlier. If there's a design change on something like a shaft diameter, you don't have to go and update the shaft and then find all the bearings and update the bearings. That process can be pushed through from that skeleton part. As you saw with this design, I changed the width of the machine, and the frame generated, base frame updated. I didn't even have to worry about that. It just updated while I was busy with everything else. And so basically it's saving you time on those manual updates. You don't have to go and double check everything. Okay, has everything updated? Do I need to go and update anything? Before release, you would still have to make sure, but you don't have to go and physically do every single little update manually. So, that brings me to a close on this session. We've got about 15 minutes left on the allocated time slot. So what I'll do is I'll open up for any Q&A and see if there are any questions that come through. There is a chat panel available at the bottom. You can send through any questions on the chat and then I can answer them as they come through. I'll give it a few minutes. If we don't have any questions that come through, then I'll do a closing off. Okay. So we don't have any questions that have come through. So I'd like to just thank you for your attendance. Thank you for, if you are watching this on YouTube, thank you for watching through the video. I hope that you've gained some good information on how skeletal modeling works, and just to get the last slide up here. If you have any more questions, we've got our 4 offices with the contact details here. You can contact your nearest office and with any questions you may have, and we'll get a technical representative to answer those as best as we can. Once again, thank you very much, and hope you enjoy the rest of your day.